start the recording as well. Okay, so housekeeping stuff taken care of. We're going to finish example 2B today. That is my goal. We're going to push on. Talking about proportional odds and non-proportional odds. What's that mean? What am I talking about? What's the difference between proportional odds models for ordinal outcomes and non-proportional odds models for ordinal outcomes? Go for it.
One of them, the proportional, means that you are using the same slopes in both models, and the non-proportional, they could be different.
Yep, that's exactly it.
I'm saying could because they could
Could
end up being
be.
the same.
Yep.
We don't know.
So this is an example of a non-proportional odds model in which each of the submodels gets different slopes for the predictors. So we're saying, for instance, GPA has a different relationship in predicting the choice of something above 0 for this outcome than it does in predicting the choice of something above 1. And these are testable. Essentially what we can do is say, what happens if I force these two numbers to be the same? Do the data get shorter? Does the model not like it? So that is a constraint that is placed in the proportional odds models that you can remove if you need to. So we looked at the output for this before. So Stata and R organize it differently, but they tell you the same information. So the Stata version, these are the slopes directly right here. So you can see now, for instance, GPA has a slope of 0.59 versus 0.72. Zoom in so you can see the numbers. So it looks like the slope of GPA is slightly more positive in predicting a choice of greater than 1 than in predicting a choice of greater than 0. Now, are those enough different that they should stay different?
Test.
Yeah, we're going to test it. You can do that a couple different ways. This table right here are the differences in slopes directly. So this is a walled test version of it, where I'm taking the difference in slope, dividing it by its estimated standard error, and I get a test statistic and then a p-value for it. That's one way to do it. So this is nice and convenient because it's provided for you. It looks like the GPA slopes are not that different according to this. The grad school slopes are not that different, and the slopes for private might be a little bit different. All right. Yeah, go for it.
Because we're trying to interpret what a gamma is, if you go back up to where you were before. So, is the beta, like, the slope for all the submodels combined, and then the gamma tells us the average distance from the beta for submodel 1, for submodel 2, and so on?
Not in this case. I'm honestly not sure what happens when you have more than 3 categories and there would be like different slopes to be compared. I'm assuming it would go through all of them, but actually what beta is in this is just a repeat of this model right here.
Which is our original model that we had for proportional.
No, this is the 0 submodel in the non-proportional odds model. So it's this one. It's just that it spits out first what is the slope in each submodel. That's this table right here. And it's labeling them based on your data. So this is the submodel of predicting something greater than 0. This is the submodel predicting something greater than 1. And these are the slopes within each submodel. Then this table essentially gets repeated as beta here. So these are the slopes for the 0 model. These are how different the slopes are in the 1 model.
So in the second one that you have here with the alternative parameterization, the one that's labeled beta is your coefficients for submodel 0.
Yes.
And gamma 2 is basically like the linear combination of 1 or of 0.
Gamma is the difference. It is how the slope in the second submodel differs from what it is in the first as the reference for the comparison. Yeah, and I don't know what these labels mean, to be honest with you. Whoever wrote the package decided they wanted to call it that. So I just looked up in the documentation, figured out what the numbers should be, and then worked backwards to figure out what this table must mean. I work backwards to figure out what things mean in this class a lot, because everybody has different terminology and different notation, and then you get into differences by software package and how they implement things, and it can be very tricky. Okay, so one way to test the slopes is directly, like these wall tests right here. You can test them as a set with a likelihood ratio test. You could also ask for a multivariate version of this, but that differs across software packages, unfortunately, so I'm not doing that. So I'm doing a likelihood ratio test against the proportional odds model in this stage. So I can see whether the three slopes as a set need to be different, and it looks like they don't. So I have two that definitely don't want to be different, one that's like a maybe. On the whole, averaged across, they don't want to be different. Now, I think I had left off last time by saying that our folks are going to have to do more typing. That sound right?
I think so.
Yeah. Such is life.
Mhm.
So I am using VGLM from the VGAM package to do this because it was the only one I could find that had both of these options. So parallel equals false means non-proportional odds, not parallel slopes anymore. The output is organized by predictor rather than by submodel. So you'll note that we have the two intercepts, the two GPA slopes, and so on. It gives you both -2 log likelihood and log likelihood. The homework system takes -2 log likelihood, so that's the one that I bolded here to remind you of that. And what are these things? Exponentiated coefficients. What have we been calling those? There we go. These are your odds ratios. E to the slope in logits.
Mm.
So that's what that means. So I have all of these things. These are all effect sizes. And one more time, if these are all positive numbers, does that mean these are all positive slopes?
No.
No. Odds ratios must be positive. So do not get screwed up in your homework by looking at the sign of an odds ratio. It's always positive. These odds ratios, these ones, are all above 1. So what does that tell me? Those are positive slopes. The one that is between 0 and 1 is a negative slope. So the differences. I recreated the likelihood ratio test that I just showed you in Stata using ANOVA. Type equals 1 gives you that particular type of test. Here's the test statistic and the p-value. So same conclusion in terms of that. Now here's how I'm going to test them individually. Yeah, you've had to do this in a few different spots. I introduced this in intermediate. You would have used this in your first homework as well to compare the effect of papers versus posters. So once again, what are in these things? What do these numbers do? They are multipliers. The order is the same order as found in your output. Okay? So what I'm doing is saying, in this comparison, leave the intercepts alone, leave the second set of slopes alone, and leave the third set of slopes alone. For the GPA slope specifically, I want to have what it is in the 1 submodel minus what it was in the 0 submodel as the reference. So the -1, 1 combo does that for me. It's literally the difference between the slopes is what's being computed along with its standard error. So in my homework, I usually have something like this versus this, and in the instructions, I say the one before the versus gets the -1 in the code. So this is consistent with the way that I talk about it is submodel 0 versus submodel 1. And subtraction is accomplished by putting the negative number. So then the second comparison does the same idea, but for the grad effect, whether your parents had a graduate degree, and then the third one does it for whether you went to private school. And so then these estimates down here are consistent with that gamma table that Stata gave you by default. So the way I would explain this is that the GPA slope is more positive in the 1 submodel than the 0 submodel. So it has a slightly bigger effect in predicting choices above 1 than in predicting choices above 0, but it's not significant. I'm using my little GLHT function to add odds ratios to the end of this, by the way, so you get your effect sizes in the same thing. And this one, the grad slope was positive, right? Yep, so they're both positive. The second submodel one is smaller. So 1.08 versus 0.99. That's why the result is a negative number. because the slope is less positive. So it's not that the slope is negative, it's that it's less positive. And for this one, I believe it actually switches sign. Yeah, so private has a positive effect in the first submodel. It has a negative effect in the second one. And the difference between those numbers is this. So it starts out at positive 2, and then it comes all the way down to negative 0.5, or 0.2 all the way down to negative 0.5. So the discrepancy is this. And I get the same, actually not quite the same. Let me show you the p-value. 0.058, according to Stata. R thinks that it is 0.0523. That is because these packages use different kinds of standard errors. And I could not find a way to fix that. So in your homework too, there's no standard errors being reported, and there's no test statistics that would change as a function of them, because they're not going to match. So you're doing likelihood ratio tests instead, because they always match. So we talked about how this would grow very quickly. If I had 3 submodels, like if I had a 0, 1, 2, 3 outcome, then how many slopes would be in this table?
One more time, sorry.
Yep. If I were predicting a 4-category outcome instead of a 3-category outcome, how many slopes would be added to this table? Say it again. We only have 3 predictors, so it would actually be just 3 more, 1 for each new submodel. And if I had a 5-category outcome, then I would be adding another 3, and another 3, and another 3. So it grows exponentially. It can be very tricky, I think, to figure out which ones are different if you have a lot of choices in your outcome, and most people wouldn't bother. However, SAS Proc Logistic and Stata Go Logit 2 have routines by which to automate the selection. You can ask it to figure out what the optimal combination is of which ones want to be different and which ones don't. So I ran those. I could not find it in R. And it came up with a hybrid.
Interesting.
Yeah. It wants private to be different. It wants the others to be the same. And interestingly, at least to me, once you force the others to be the same and the only one that's allowed to be different, then the difference is indeed significant. So the inference changes. However, if I look at what the slope is, it's non-significantly positive in the 0 submodel and non-significantly negative in the 1 submodel. So these 2 slopes are different from each other, but neither one is different from 0 in the first place. That can happen. That's the worst kind of interaction term to try to explain, by the way, is these null effects are in different directions. So if this were my analysis, I would probably interpret this as I don't need this in either submodel. It's not helping to the prediction. Whereas these ones are helping, and they're helping to an equivalent extent. There we go. So in R, how to do a hybrid model is you tell it false-ish, then you add a squiggle, and you write out the variables for which you want parallel equals false, meaning let their slopes be different. So last time I didn't have this part on there, and it made them all different. Just by listing this one, it's only going to make that one different.
So just making sure I know, so since I use R, I would have to choose 2 different models maybe to figure out what the best predictor is, and then I can make that comparison based off of my negative 2LLs.
Yeah, if you wanted to do all possible ones, that would be a lot of coding. I think
Right, I'm
yeah.
just saying, you know,
Yep.
but just realistically, you would have to do that where they're either all parallel to all combinations of 2.
Or I think a reasonable compromise that would reduce the amount of complexity would be to just compare adjacent ones.
Yes.
Like, is 1 different than 2? No. Okay, let's put those together. Is 2 different than 3? Let's put those together. Because I don't know how useful it would be to find that, like, the first one and the last one are different you know, like there's combinations that would not be as useful. I think at that point, though, if you start to see a lot of evidence that the slopes want to be different, that you would
Just
want
ma-
to
just
switch
make
to
it
a
all
different
different.
model. Just make it nominal, yeah. Because this gets to be very difficult to explain, quite frankly.
Mhm.
So,
Okay, thank you.
sure. And that one is different, so there we go. Now, pictures. What does this model tell us? In order to make pictures, we got to do a little more work than usual. Oh, someone's excited about this. Now, like, ooh, code. So I've got a couple different things here. Stata users, you don't have to do very much typing at all. Margins. So I'm saying the first number is where it starts at, the second number is what increments are, and the last number is where it ends. So I'm saying print estimates for predicted outcomes starting at GPA of -1 in increments of 1 up to 1. GPA is centered at 3. That's why I have these values like this. So I'm asking for predicted outcomes for somebody who has a GPA of 2, 3, or 4. That's what's happening here. Likewise, I'm asking for predicted outcomes as a function of whether or not their parents had a graduate degree and whether or not they went to private school. Predict XB is not the default, I believe. That means print the predicted outcomes in the model scale in logits. That's what that means. If you take it off, then you get predicted probabilities instead. Remember that model scale, data scale? Model scale is in logits or probits. Data scale is in probabilities. And then you can throw these into a plot quite readily with margin plot, I think it is, something like that. Our folks have to do a little more work. So the first thing I'm doing here is creating a series of fake cases.
So that's 9 individuals,
This is 12
or is that?
combinations, I think. Because I have 3 GPAs by 2 by 2. So 12 points altogether is what I'm creating. So I'm creating a variable called GPA3, and this person has a 2, this person has a 3, this person has a 4. Then I'm going to repeat that pattern. And then the first person is going to have no parents going to grad school and went to public school. And then I systematically vary the zeros and ones so I hit every possible combination. The reason I'm doing this is because I want to show the effects of all 3 predictors, and I need them to be organized in this way so that all possible combinations can be shown. If I go into the data set and start generating predicted outcomes, there may not be people in every possible combination. So I'm creating a data set of fake people for the purpose of plotting them to show what the model looks like. So these are just 3 objects, columns of data. I am creating then a data set for them. The data set is called FP. Do you know what that stands for?
Fake people.
Fake people. Yes, this is what I call it. That's what they are. So building a data set then with the data frame option, the column is going to be called GPA3, and in that column is going this series of numbers right here. The next column is going to be called grad, and it's going, these numbers are going into that, and then the last column is called priv, because these are the names that are in my data set. Now, I can generate predictions from the model. So I'm saving a new object that holds the predictions, pred CPO for the proportional odds model, from the fake people, adding a column for Y, so this is in logits, by going into the model that I just saved and saying, use this model result to generate predictions for these fake people in the linked metric. So it's using all the coefficients from my model results to build predicted outcomes for these sets of fictitious people in logits, type equals link. And then I made a second column it's going to generate called yprob, which stands for probability. And I know that it's going to be a probability because type equals response is the data scale. So predicted logits and predicted probabilities is what I'm generating for these 12 fake people from my last model. Okay, are you with me so far? At least conceptually. Ish. The result is columns named things like this. Like, what?
Sorry.
The what? No. So I figured out how to rename them. So the model is directly predicting the logit of a response greater than 0. That's one prediction. And the predicted logit of a response greater than 1. So what results from this process is shown right here. Here are the values of my fake people. Here is their predicted logit of answering greater than 0. Here is their predicted logit of answering greater than 1. And then the type equals response part added these. This is a hell of a lot more interpretable. This is the probability of each answer choice, the and. So somebody who has a GPA of 2, whose parents did not go to grad school, and who went to public school, has a probability of 0.76 of saying, nope, not going. They have a probability of 0.17 of saying maybe, and they have a probability of 0.068 of saying, yes, going to go to grad school. So you can throw these in bar charts, you could make line graphs or things, whatever you feel like doing. I typically use line graphs because that's what I sort of think as. But these are the probabilities that result from first translating these predicted logits into predicted probabilities, and then subtracting between them to get the missing answer for 1. Let me remind you about that part. I have a slide about that. Way back. Way back. Where is it? Oh, no. Not that far back. I apologize. Here it is. This is the idea. This is slide 31. So if the logits directly tell me about 0 versus 1, 2, 3, and 0, 1 versus 2, 3, and 0, 1, 2 versus 3 in this example, then I can get the middle probabilities through subtraction. So if the model tells me this part, which is what it's telling me, 1 minus that has to be what 0 is. So I can get that with this. Likewise, this last submodel is directly telling me what the probability of 3 is, so that's that. The middle ones are implied. So to figure out what the probability of a 1 is, I start with this probability of 1, 2, 3, and then subtract from it the probability of 2, 3. And that leaves me with the probability of just 1. Same thing here. I have 0, 2, 3, versus 3. I subtract that from that, and I get the probability of a 2. So that's what it's doing for you in generating these predictions. It's figuring out what the predicted logit is for the submodels, converting those to probabilities, and then doing the subtraction to figure out what the probability is for every possible category. A little tricky. And I see the Excel file online for the plots below.
Oh my, yes.
These are my plots. Yes, you can make these in R. Yes, you can make these in Stata. I wanted to show more of like the algorithm of how you get to the point where you have something to plot, because that's the hard part. So what I have here on the y-axis of this plot is the logit of greater than 0. And I've put in not going to grad school in here. So that's what this model is predicting. We're focusing on just the decision of saying maybe or yes, but not no. So as we might expect, as GPA is higher, you're more likely to say something other than no. That is shown by the slope of the lines. Then I have chosen colors and patterns to convey the other two. So blue versus red indicates whether or not your parents have a degree, and dashed versus solid within the colors indicates whether you went to public school or private school. So you can see that red versus blue matters, like whether or not, blue is higher, so people whose parents went to grad school are more likely to say something higher than no. But within the colors, there's not much difference. So that's the effect of having gone to a public school instead of a private school. So these lines are straight. These lines are straight. But I'm plotting the model in which the effect of private gets to be different across submodels. So look, it's negative and very small in this one, and it's positive and bigger in this one. It's not significant, but it's bigger.
Are these using proposition or proportional?
It is using the last model, I think, the hybrid one, if I remember correctly. Yep. Yeah, the hybrid one.
Private school is non-proportional.
Right. Yeah, so GPA, the slope is the same. Back out again. The slope is the same in this picture and this picture, because GPA slope is the same across submodels. The distance between red and blue is the same across these, because the effect of graduate degree is the same. But the difference between dashed and solid is not the same across submodels because the slope of private wanted to be different. And that would be a whole paragraph, like in your thing. Now, logits are not going to be very helpful to most people. So then we take the predicted logits and we convert them into probabilities. And so this is displaying exactly what the submodels are predicting. Not the probability of each category, but the probability of something greater than 0 for the first one up here, and the probability of something greater than 1 down here. So these are starting to look a little bendy, and these ones are definitely a little bendy. Coincidence or consequence?
We didn't test that.
Yeah, we didn't test any quadratics or non-linear slopes.
I think this is what logistic regression does.
Yeah.
Is that in the model scale, it's linear, but once we convert it back to our data scale, it looks like it's S-shaped. And we just have a portion, so we're not seeing the whole S-shaped range. And maybe
That's
that's
right.
not visible in our data, but it can be better.
Yep, so basically the probability of saying, yes, I'm definitely going is very low. So we're hitting close to that lower asymptote. So this is the lower half of the logistic function we're seeing here happen. So even though we didn't put any quadratics or any non-linear slopes in the model, you end up with it as a consequence of the back translation from logits to probability. So let me find the picture that goes with your words. I know that one's in here. I just got to find it. One of the first ones. This one. That's what we're seeing. And I literally made this picture this way. I plotted logits on the left, and then I turned them into probabilities on the right. And so we're seeing the bottom half of this curve show up in our example. If we had people who were definitely going to graduate school, then the same thing would happen on the top end. It'll level out here. Consequence. Here's a pro tip. Vladimir, is the answer ever not consequence? He's laughing. It's like, nope, the answer is always consequence. Always. Always consequence. I say, is this a coincidence or a consequence? Is one of my ways of asking questions, and the answer is always consequence. Yeah. So if proportional odds falls apart, or you have a nominal outcome for which it doesn't make any kind of sense to have this cumulative lumping together, we can do nominal. Your last model in your homework 2 is nominal.
Mm-hmm.
2 slopes, no interactions though. That's it. Because the whole point of homework 2 is to figure out what y is, not what x is.
Mm-hmm.
Do we have the strength to see a couple nominals?
Yes.
Like 2? Because then we can really be done
Yes.
with this unit? They're like, no. You're the only one who has the strength, I guess.
Question before
Yeah.
we move on. So
Go ahead.
technically, not saying you would want to or if it would be real meaningful, but we could test the GPA versus the I could test between the various variable slopes also. Yes, with our negative ones and our ones, if I
Yes.
desired.
Yes.
Okay.
Yes, you can compare any kind of slope that way. However,
It's like, but what would be meaningful?
Yeah, that's what I was gonna say. So, like, if you think of it as, like, what is the relative benefit of different advantages?
Mhm.
So having a parent who's educated is an advantage. Having gone to private school is presumably another advantage. Which is the bigger advantage? You put a negative one on this and a one on that, and then you can compare them with this same technology. You'll see this, like, there's a lot of instances in which you need to do this in different contexts, but this is how you would do it. Now, I don't think it would be meaningful. Like, it will spit out the number for you just fine, but I don't think it would be meaningful to compare, like, this slope and this slope, because GPA is per unit GPA,
Right.
as opposed to grad, which is 0 to 1 as the entire range. So that's where it gets weird. If you wanted to do something like that, you'd have to standardize your variables to be the same scale.
Okay, thank you.
Yeah, so, sure. Other questions before we look at nominal? Nominal is in some ways easier and harder at the same time. That's what I'll say. There's aspects of both. First up, empty model. What are we predicting?
Your reference model? No.
Yeah, a reference category.
Category, sorry.
Yep, so
Sorry.
just to review, how nominal works, back to the slide for it again, is this one, right here. We're talking about the last one here. So rather than having each submodel include all the categories and lumping them together in this lower versus higher kind of way, we are saying I'm going to pick one of my categories as the reference one, and each submodel is going to tell me about a choice of a different one relative to that reference. This is analogous to dummy coding, but for the Y side, not the X side. Same deal. So you can choose what your reference is. If you don't choose, the software will default to something, but you can override that default. And I tried to do that, and at first my numbers didn't match. And then I figured out that the way you tell it to override it is different than SATA and that isn't R. So,
Yay.
yeah, more fun. So the first submodel, I am picking, by the way, 1 as my reference. The middle one. Now that may sound weird, but to me, it makes more sense to think about 0 versus 1 as 1 mon and then 1 versus 2, as opposed to 0 versus 2. That one is less interesting to me. So my first submodel is going to predict the probability of answering a 0 instead of a 1. My second submodel is going to predict the probability of a 2 instead of a 1. So note the other choices aren't in here. So these are conditional. That's going to make it a little bit tricky. And you get intercepts by default, not thresholds, so they're already going the right way, and all the slopes are separate by default as well in these models. You could constrain them to be equal, but that often is not a thing. So first off, we are going to predict apply 3 using the middle category as the reference. This is M-logit in Stata. M stands for multinomial. In fact, that's what it's calling this, a multinomial logistic regression. I don't like that terminology. Do you know why I don't like it? Anyone care? What distribution are we using for these models?
Binomial?
It's, well, Bernoulli or
Oh, binomial,
binomial
sorry.
for binary. What distribution did we use for ordinal? Do you remember? Let me go back to that. That's the link. Yes. So in generalized models, we have different link functions that deal with boundaries in different ways, and we have different conditional distributions for what the data should look like. So we're not using normal. When we did binary, we switched out to Bernoulli. When we did ordinal, we switched it out to essentially Bernoulli for more than 2 categories. It's called multinomial. When we switch out the link function to baseline category, we're still using a multinomial distribution. So the terminology is unnecessarily confusing. Regardless of what model you're fitting to your categorical data, you're using the multinomial distribution to do it. They differ not in distribution, but in links. Ordinal is cumulative, adjacent category is partial credit, and baseline category is nominal. So to call something a multinomial regression doesn't actually tell you what you're doing. But unfortunately, that is the most common way of describing this. I would call this a nominal regression model. Stata calls it multinomial, and that's why this is an M. Base outcome. The number that goes in parentheses is in your data, which category value you want as the reference. So I have 0, 1, 2 in my data. I pick the 1. In R, I put a 1 in here, so I'm using VGLM still. Family is multinomial, and ref level with a capital L is 2, because choice number 1 is the second choice. That's why. So when I first ran this and I tried to get it to work, I put a 1 here, thinking, well, I want the ref level to be 1, just like I told Stata to do, and nothing matched. So then I started playing around, and I figured out that 2 was the correct answer, because 2 is the second choice in my data set. So this is confusing.
May I mention one other thing that could be confusing when you're doing your assignment? If you have the wrong reference level, you can still get the right deviance number.
Yep, because it's an alternative version of the same model. Yep. Reverse equals true means I want intercepts. And then otherwise the formula looks like just a standard empty model. So let's go back up to Stata output first for this. So it looks a lot like the way that we had the output organized for ordinal. I've got a 0 submodel. It helps me by saying this is the reference. That's very nice. And then I have a 2 submodel. So the first one is predicting the logit of the probability of answering 0 instead of 1, a lower choice. The second submodel is predicting the logit of the probability of answering 2 instead of 1, an upper choice. So that means, logically speaking, our effects should go in opposite directions across the 2 submodels, because the first one is predicting a response of less enthusiasm of going to school. The second one is predicting a response of more enthusiasm. So they're oriented backwards from each other. That is something that makes it tricky. And yes, I have a comment here that the -2 log likelihood for the empty model is exactly the same as it was for the empty ordinal model. Because all these link functions are doing is ensuring that the model at the end of all of this predicts the probability of each category. The submodels just divided up differently based on ordinal versus nominal. It's the same likelihood. So Stata then puts them back together for you with margins. And it gives me the probability. And those are the ones in the data. Well, that's nice, except this doesn't match my model. So this took me a minute. And when I finally figured it out, it was one of those like, oh, I get it now. But it took a minute. So here's how this works. The coefficient in logits for the first submodel, predicting the logit of the 0 instead of a 1, is 0.45. How do I make that a probability? You remember?
EXP.
E to the logit over 1 plus e to the logit. When I do that, I get an answer of 0.61. 0.61 does not match any of my probabilities in my data. So I was like, huh? Well, let me try the other one. The logit of -1.2 for predicting a choice of 2 instead of 1 becomes a probability of 0.22. Now, where did those numbers come from, was my first question.
Should those be opposite? No. No.
They're
something different.
conditional. So the thing you have to remember is that not every category is in every submodel. So these are probabilities excluding the people who answered something that's not of interest and their percentages. So the way this makes sense is the first submodel is just these people. So the denominator of total is 0.9, because 90% of the people answered 0 or 1. So what is the probability of answering 0 instead of 1? Well, the probability of answering 0 is 0.55 according to our data, but it's 0.55 out of just these two sets of people, and that's where the 0.61 comes from. It's a conditional probability. Of the people who answered 0 or 1, 61% of them answered 0. I'll say that again. This number is telling me that of the people who answered 0 or 1, 61% of them answered 0. That's the reference point for this model, the intercept. Likewise, the people who answered 1 or 2 are in the second submodel. That's only 45% of the data. So the probability of answering a 2 instead of a 1 is 0.10, the number of 2s, out of the 1s and 2s. That works out to be a probability of 0.22. So these are conditional probabilities excluding the part of the sample that's not in the submodel. That's tricky. Okay, does that make sense, or do you want to hear more or again?
Maybe give us like an example, like theoretically, yeah.
Of when you would use a nominal model? Is that what you're asking? Or how the parameters work? How the parameters work. The conditional probabilities. So conditional means like part of it is not being represented. So this derives from the fact that we didn't have this problem in the other models at all. Everything was straightforward because all categories are represented in all submodels. That's why. So you didn't hear me say of the people who answered this as a precursor for what the denominator is going to be, because the denominator is 1. The same thing happens in adjacent category. Anytime that you're not using every category in every submodel, your probabilities are reflecting just the people that are in the submodel. That's why. So with that lens in mind, let's revisit the table. Probability of a 0 answer is 0.55, a 1 answer is 0.35, a 2 answer is 0.1. So the first submodel is picking 0 instead of 1. Out of the people who answered 0 or 1, which is 0.90, the people who answered a 0 was 0.55. So 0.55 divided by 0.9 is the 0.61. That's what my intercept is telling me. The first submodel is excluding the 2s. The second submodel is excluding the 0s. Same result.
So which one would you work in the model, or in the theoretical paper?
So I think it depends, but at this point, I'm just trying to figure out how the submodels are organized and verify that against the data. When you're talking about reporting the results of these analyses, like in the next model, we'll have slopes. You have to talk about the slopes in relation to the submodel, because that's how they're operating. They're predicting the probability, helping to predict the probability of a 1 instead of a 0, or actually, nope, 0 instead of a 1 in this, 2 instead of a 1. They're helping to do that. But when you're trying to show the end result of your slopes, like how do these variables fit together to generate a prediction, then I think breaking it into the probability of a 0, a 1, or a 2 makes more sense. That will be easier for your reader to hang on to. My opinion. Okay. So our output for this is the same. So here are the logits of 0 instead of 1 and 2 instead of 1. And then it tries to help you. Does this help anyone? The name of the linear predictor is log of mu comma 1 divided by mu comma 2.
Is mu the mean?
Yep.
The mean of 1 versus mu divided by mu 2?
It is, mu is, it's got to be referring to, like, that's got to be an odds for this to work, the log of the odds. But then the comma 1 and the comma 2, and then this is the 3 and the 2. This is how I figured out what had happened when I saw this, is because it's not paying attention to your data. It's saying this is the first one, the second one, the third one. Whereas my data say 0, 1, 2. So they're naming this as 1 instead of 2 and 3 instead of 2, which made,
So they're naming that as the submodels
Mhm.
rather than the choices.
they're naming it as
Your
this,
data is 0, 1, 2, your submodels are 1, 2.
yep. Actually, let me say that backwards. My data is 0, 1, 2. They are essentially recoding it into 1, 2, 3 against my will. But the submodels are organized the same way. Okay. Slopes by submodel. So I'm throwing in the same predictors that we've been working with. They by default get different slopes across submodels. There's no lumping them together. So if we look at the 0 submodel, the GPA slope is negative. That is expected. Because the first submodel is representing a choice of lower than middle. We're predicting people who say no instead of maybe. So the higher your GPA, the less likely it is you're going to say no to grad school. Whereas GPA in the second submodel is predicting a higher choice, in this case of saying yes instead of maybe. So GPA should be positively related to saying yes instead of maybe. So because of this difference in direction, to compare these, there's an extra step. So GPA slope, if I just look at the number, 0.45 versus 0.48. Those are pretty close. But they're opposite in sign, because one's predicting a lower choice and one's predicting a higher choice. So if I want to take their difference and test it, like which GPA matters more kind of thing, I have to flip the sign to make it make sense. So in the comparisons, like the state of Lincom, I have both slopes being multiplied by 1 rather than one of them being multiplied by -1. That flips the sign so that the submodels are internally consistent in terms of predicting the same direction. Stata prints odds ratios for these, but they call them relative risk ratios. I don't know why, but that's just a change in terminology. It is e to the slope still. In R, the weirdness is accomplished by ones. So previously this was -1, 1, -1, 1. By putting the ones in here, I'm flipping the sign, and then it turns into subtraction like I wanted. Yeah, so it's a little tricky. And the output is again organized by variable rather than by submodel for the nominal models. But otherwise, it tends to agree.
Can you explain, I'm so sorry.
No, don't apologize.
Because for the ordinal model,
Mm-hmm.
you put in, like, one of your coefficients should be a -1, one of them should be 1. So
Right.
you're subtracting it.
Yes.
But for nominal data, you're not going to use negatives when you're entering which things to include. Is that because in the ordinal data, if you use the cumulative submodels, you've already included like 0 versus 1, 2.
Mm-hmm.
So you're like basically subtracting the 1 when you try to obtain that number. And then when you're looking at the nominal data, it's 0 versus 2. So the model that you used has already gotten rid of the ones, you don't even do the subtraction.
So and this is, the result of this needing to be a 1 instead of a -1 is a special case of the fact that these categories are not truly unordered. They're still sort of ordered.
Okay.
So if these were just 3 different things and there was no ordering, then I wouldn't need to flip the sign because I'm just predicting each thing. But because of the way that I set this up, I chose to have the 1 as the reference. So the first submodel is predicting down the ladder, and the second submodel is predicting up the ladder. So to orient them to the same direction, I flipped the bottom one in sign.
So, right now we're looking at an example which just has 3 possible outcomes.
3
But if
outcomes.
you had 4,
Yes.
would it be like, so if you had 0, 1, 2, 3, and then the reference group was 1, then for 1 it would be 1, for the other one it would be 1, and then for the 3 it would be 2?
No, it's day 1.
Oh,
Yes, the reference stays the same across submodels. So if I had 0, 1, 2, 3, then the first submodel would be picking a 0 instead of a 1. The second one would be picking a 2 instead of a 1. And the third one would be picking a 3 instead of a 1. So if what you really want is those adjacent differences, like you just described, a 2 instead of a 3 instead of a 4, like that kind of thing, that is the other link function. That's the middle one here, adjacent category. I do that one instead. Because if you have something that's ordered, like skipping across categories probably isn't as meaningful as looking at adjacent ones. Nominal is really designed for like unordered events. But I'm using it for ordinal just to make a demonstration. So there we go. And because this would break people's brains, I'm plotting it as if it's adjacent. So I'm going through the same process of generating outcomes to do this, renaming them. So the submodels directly predict the logit of a 1 instead of a 0 and a 1 instead of a 2. Or actually, 2 instead of a 1. I'm going to flip one of these so that it works out to be more understandable. So here's my picture revised. So I have the logit of no versus maybe, or as I abbreviated it here. And then I have the logit of maybe versus very. So these pictures are oriented in the same direction. That way it becomes easier to explain. But we see the same tendencies towards bendiness in the probabilities at the bottom here. So same story. And here's a result section that you can use for your future reference. Okay. I'll move that back for a second. So nominal, take-home message. What's my take-home message for nominal?
they're not ordered.
They're not ordered. You can use nominal for ordered, but they don't have to be. One category is the reference. The model compares each other one to that and only uses the data from that comparison for each submodel, not cumulative. Question?
2 questions.
Yeah.
First one, so if our reference category in this situation was 1, well, it was 0 instead of 1,
Yes.
then we would have had to use -1 and 1.
Yes, like if you wanted to know if the relationship of a variable in predicting the 2 was greater than in predicting the 1, both
Yes.
relative to 0, then it would be -1 and 1 because you're heading up in both of those.
Gotcha. And so then on the flip side, if you used 2 as your reference category,
2 is the reference, then
2 is your reference, then would you still use like a -1 and a 1 or no?
yeah, because the negative
Because
1
you're
and
still
1 is
going-
anytime they're going in the same direction, essentially. You're predicting
Okay,
down the ladder
I'm
or
just-
up the ladder.
I'm just making sure because, yeah.
Yes, but if you're mixing them, if you're doing
Like,
this,
like,
then you
if
got to flip
like,
one.
if you have 5 categories and you pick 4 and you're
Yeah.
doing,
Yeah, at that point it gets hard.
yeah, okay.
And I think if this becomes overwhelming, like you can sort of break it into pieces. Like there's nothing that stops you from running just a binary logistic model on 2 of your answers. And whichever 2 you want to compare. if it doesn't show up, because you can work your way backward to get a comparison across any of these. It's implied by the model, but it might be easier to break it into pieces, because that's essentially what happens. I wanted to talk about just one more very brief thing that I didn't get a chance to say. One slide, and then one wrap-up slide.
Yeah.
And we're done with Unit 2. We really are. We really made it. Effect sizes. So this is slide 40. One thing that I often see in logistic regression for binary outcomes is some kind of measure of prediction quality by rounding predicted probabilities into zeros or ones and then doing like a chi-square cross tabulation with the real zeros and ones. That is kind of cheating because there's more error to it than that. So there's an alternative way if you wanted to do something like that that I would recommend and I've described here. Essentially what you would do for binary data to show how related it is to the real ones is to start with generating a model predicted probability. That step is the same. But then rather than rounding it to 0 or 1 and assuming that it's perfect in that regard, we would draw a random 0, 1 variable from a distribution with that probability as its mean. So in software, there's distributions that you can draw from. And then, like if I have a probability of a 0.9 and I draw a random number from a distribution with a mean of 0.9 for me, I still have a chance of getting a 0, even though it's not likely. So it maintains the error in the process that way. So that's how I would get predicted zeros and ones to either correlate or do some kind of relationship with the real ones to get a sense as to effect size. The same thing would be true in categorical. You would start by generating a predicted probability of each category and then using those as means to draw a random draw from a multinomial distribution with those means. And then you have error in the prediction. So I would not do any kind of effect size that involves rounding because it's sort of cheaty. But that's what I'm going to say about that. Okay, wrapping up then. This was our first generalized unit. The next one's going to be a little easier. I promise. I know, this is the worst one. Get it over with. So comparing generalized models for conditionally normal outcomes, like the world of general linear models versus where we're now. What's being predicted directly? In standard regression, it's just y. That was the end of the story. Because we used an identity link, meaning y times 1. And the inverse link would be y divided by 1, so still just y. Now we're in logits and probits, something that transforms the probability to be predicted into something that's more continuous, so you don't go out of bounds. What estimator are we using? Ordinary least squares in general linear models, which is also equivalent to residual maximum likelihood, if you've seen that in the longitudinal or cluster data classes, and a normal conditional distribution. Now we're using maximum likelihood, which is a slightly different version. It's iterative and multinomial. Bernoulli is a special case of two. How did we assess global and specific effect sizes? We had a true R-square in standard regression. We could compute D's and R's. We could compute indices involving R-square, like semi-partial. We could compute standardized slopes. Here, we can sort of have an R-square, but there's a million of them and they disagree. You can also convert things to odds ratios, but as we've discussed, they're still in units, so they're not really standardized effect sizes. And can you compare fixed effects between models? In regression, you can. So if I have a set of predictors and then I add another predictor to my model, I can see how the first set of slopes changed, and I can talk about that. Like, oh, the relationships are smaller after I control for this other thing, or the relationships were significant and now they're not. I can do that. You can't do that in these models because they change scale. When you're predicting a logit, no matter how well you predict it, the theoretical variance of it is 3.29, pi squared over 3, and that number can't change. So in order for the model to adapt, essentially it has to think about what the variance would have been in order to still have 3.29 left. So as you add predictors, the model implied variance grows rather than shrinks. And that means the predictors are on different scales across models. If you wanted to compare them, you'd have to convert into the same scale, and that's what these older papers are talking about if you're interested. I don't usually bother to do that. But just keep that in mind as something that is a little bit tricky in practice. You can't compare across models. They're not on the same scale. There. 308, we did it.
Yay.
Question.
So looking at the effect sizes, it seems like there's no really ideal way to report an effect size for
Nope.
a generalized model for analytical outcomes. But sometimes we still want to do that. It seems like odds ratios are probably our best option.
Mm-hmm.
But they're not easily comparable to each other. So is there a way that we can kind of convert our odds ratios into a standardized metric after we obtain the odds ratio? Can we do that?
So the question was, effect size is dissatisfying in generalized models. I'll just say it that way. Like, there's cons about all of them. There's nothing that's nailed down that we can all agree on. Odds ratios and whatever they want to be called, and other relative risk ratios, e to the slope, point being, odds ratios, they suffer from the problem of lack of comparability of units. And so rather than fixing that on the odds ratio side, you could fix it on the variable side. If you had to standardize the variable, but in a different way. So you could z-score everything. That'd be one choice. Or you could take a continuous variable and fit it into the range of 0 to 1. Like, make the lowest score 0 and make the highest score 1. And then it's on a 1 unit change, just like your binary predictors would be. And then your odds ratios are on a comparable scale.
And you're standardizing the predictors or standardizing the outliers?
Standardizing the predictors.
Standardizing.
Find some way to make their units comparable.
Okay.
And then your odds ratios will be comparable as standardized effects.
I understand the discussion.
Okay. Other questions or answers, as it were. So let me tell you why the next unit is going to be a little easier. Log, the end. We're going to be predicting counts. The link function we're going to use is the natural log. So we predict the log of the count. Done. No more submodels. Just log count. However, in categorical data, there's not a question as to what distribution you should use. It's Bernoulli for binary, it's multinomial for 3 or more categories, the end. In count data, you have to answer the question about what kind of distribution you need, because there are kinds, and we need to see which ones fit relatively best. And that controls how much variance is expected in our model, which controls the size of our standard errors and our inferences. So that's going to be the new part, is figuring out what distribution is the rightest one, but doing it without having to worry about what the model is predicting. It's log count the end. So I think it's a little easier, but we'll see, right? Nothing is easy the week before spring break. That I can tell you with certainty for any of us. But
Question.
yes.
So when we were, this goes back to finding the 0.61 and the 0.22.
Mm-hmm.
Is there a nice way to change those into the probabilities without doing a system of 3 equations and 3 unknowns?
Yeah, once you can get back to the marginal probabilities. Like, that's what Stata does for you, is essentially figures out what the implied probability would be for all of them.
Well, right. But is that essentially what it's doing though for us? Is it doing a system of 3 equations to change that out for us? Or if you don't know, that's okay. I'm just curious.
I'd have to look. I don't
Okay.
know off the top of my head.
Okay,
But I know that it's doing the math needed to figure out what the probability of each is, even though each is not part of each submodel.
Right, because I was
It's
like,
working
I'm
across
like,
them.
okay, if I'm trying to work backwards, well, I got 3 equations and 3 unknowns here. But, I just curious.
Yeah, I'd have to look up what they're
Okay,
doing.
no worries.
Okay. Any other questions?
A comment,
Or comments? Yes?
that pi r squared over 3 is twice as much as the sum of the reciprocals of the squares of the positive integers.
Okay. I'll pretend I understood what you said. Pi squared over 3 is 3.29. That's the variance of logits. Okay.
Sorry.
The variance of probits is 1. That's what I know. All right, then let's see. What do you have to do? You don't have anything due Monday. Your next homework is due Friday of next week. But let us know if you need any help, okay?
Bridge activity.
After break.
After break.
After break. Yep, it's up if you want to get started on it, though. But you won't be able to do the second half of it yet, unless you look ahead or look at what we did last year. So, all right, thanks, folks. See you in next week.